So this is a video about the composition theorem for integrals. Before I get rolling, one word of warning. I think that the proof of this theorem is one of the hardest proofs in the course. And so rather than go through it in the usual straightforward manner, I'm going to go a little bit slowly, and I'm going to do the proof in some sense a little bit backwards. If you'd like, you can of course look it up yourself and find a proof that's written in something closer to the usual style. All right, with that out of the way, let's get rolling. The statement of the proof itself is long, but I guess not terribly difficult. I fix two subsets I and j of the real numbers, and I fix two functions, one f from I to j, the other g from j to r. I'm going to assume that f is integrable, g is continuous, and that j is compact. And the conclusion of the theorem is that the composition g composed with f, which goes from I to r, is itself integrable. Now, we've seen theorems that look a little bit like this before, right? We certainly know that if, say, f is integrable and g is integrable, then f plus g is also integrable, right? So we have a way to go from two integrable functions to a new integral function. But this one's a little bit messier, right? Compositions are more complicated than addition, and we're going to see that the proof is more complicated as a result. All right, let's get started on the proof. When we normally prove a theorem along these lines, right, we want to check that g composed with f is integrable, and we really have one condition for that, right, which is the condition that for every epsilon greater than 0, the upper bound u of p comma g composed with f, and the lower bound L of g composed with f comma p should be close to each other, right? For every epsilon, we should be able to find a partition so that the upper and lower bound functions are within epsilon. And so the usual way that I would start a proof would be to say, okay, fix some epsilon greater than 0. And then, of course, because I prepared these ahead of time, I could then say, let delta be, some number that I've made up, which is going to work out in the end. And then I'd go through and everything would sort of cancel nicely, and I'd end up with the bound that I wanted at the end. And when the proofs are short, I think there's nothing terribly wrong with presenting them in that sort of slick way. But this is a little bit of a longer proof. And so rather than do that, I'm going to try to go through the argument in the way that I would probably try to figure one out when trying to do something along those lines. And so rather than saying fix epsilon and let delta be whatever, I'm just going to do some calculations. And the first thing we should think about when doing a proof like this is, what do we want at the end of the day? Well, we need to check that g composed with f is integrable. And what that really means is we need to find some partition, p, so that the upper bound on g composed with f and the lower bound on g composed with f are very close to each other within epsilon. So we need to find some good partition. And if we look at our assumptions, well, we have a lot of assumptions, but the only one that tells us anything at all about a partition is that f itself is integrable. And so we sort of know, well, the only possible route for the proof is to take a partition that's good for f and check that it's going to be good for g composed with f as well. So we're just going to do that and start seeing how good a partition is for g composed with f in terms of how good it is for f itself. So I'm going to fix some partition p. And I'm going to define these four sequences, lower ai, which is the infimum of f of x over the part of the partition from xi minus 1 to xi, and then these three other numbers, capital ai being the same thing, but the supremum, lowercase and uppercase b being the same thing, but for g composed with f instead of f itself. All right. So if we're looking at the lower and upper bound functions, right, then we have our function f, we have some point xi minus 1 and xi, right, then little ai is going to be the lower bound, and capital AI is going to be the upper bound there, right? So that's what's going on. These AIs and BIs are upper and lower bounds for this partition P for the two functions that we're interested in. And what could we hope? Well, if our partition is going to be good, what we really want is that AI minus AI or BI minus BI are going to be small, right? That's what it means for the partition to be good, for the lower and upper bound, in some sense, to be close to each other. And at first glance, we might think that actually life is going to be easy in this proof, because certainly, if you want to make capital BI minus little bi smaller than some fixed epsilon greater than 0, well, you can always do that by forcing capital AI minus little ai to be smaller than some delta depending on epsilon. That's what it means for g to be continuous. So in some sense, if AI, capital AI minus lower ai is small, then also capital BI minus lower bi is going to be small. But unfortunately, the condition that, that f is integrable doesn't quite tell us that we can find a partition for which these things are all small. The only thing that it tells us is that this sum here can be made very small. Okay, so let's go into the details and see why those two conditions aren't really the same thing. So let's fix some epsilon greater than 0, and let's assume that we have a partition so that this sum here is less than epsilon. We want to figure out, does that mean that all of these terms here are in fact less than epsilon? And the answer, unfortunately, is no. Even if a is 0, b is 1, and xi is I over n, so this is sort of the simplest possible partition of the interval from 0 to 1. In that case, there could actually still be up to n times epsilon values of I, for which ai, capital AI minus lower ai, is bigger than or equal to 1. Okay? So let's put all of that together again just for a second. Even in this very simple situation, right, where our partition is a uniform partition of the interval from 0 to 1, it's actually possible for this sum to be small, to be less than epsilon, and yet for there to be a very large number of values of I, in fact n times epsilon of them, for which capital AI minus lower ai is bigger than or equal to 1. That is certainly not small. And the critical problem here is that even if you let epsilon go to 0, you can't guarantee that the size of p, that is that n times epsilon, is going to go to 0 as well. Because remember, as epsilon is going to 0, you need to get a bigger and bigger partition for this condition here to hold, right? As epsilon is going to 0 and the partition is getting better and better, in general it's going to have more and more terms. And certainly it's possible that the size of p associated with some particular value of epsilon could be epsilon to the minus 1, or even epsilon to the minus 10, or epsilon to the minus 100. In which case actually a very, very large number of indices I are going to have this bad property. Okay? What does this sort of calculation tell us? It tells us that these bad indices I, for which this happens, aren't something that you can ignore. In their proof, they're not going to go away, and so we need to actually have some strategy for dealing with them. And the strategy for dealing with them is, I think, the thing that makes this proof harder than most of the proofs that we've done so far. Most of the time when we're sort of trying to compare two things, when we're looking at compositions of functions, you can just sort of say, well, everything's getting small at the same time. We can sort of ignore things errors that are large. But in this case, there are some non-ignorable large errors. And what we have to do is we have to deal separately with the indices I where this bad things happen, and the indices I where this bad thing doesn't happen. Okay, so that was a heuristic. Now let's actually talk about what we're going to do. We're going to consider some delta greater than 0. I'm not going to nail it down what it is yet. For every delta greater than 0, I'm going to define the good sets for the partition P and this number delta to be the indices I for which capital AI minus lower ai is less than delta. So these are good sets, right? That is, these are the ones where my upper and lower bound are close to each other. And then I have my bad sets, B of P delta, which are, well, everything else. Okay. And now we can do a calculation and start figuring out, well, what happened in terms of these good and these bad sets. So I write down my upper and lower bound functions. This is the thing I'm interested in. Upper of g composed with f comma p minus lower of g composed with f comma p. Okay, we know what that is. It's just given by this formula here, sum I of xi minus 1 times capital BI minus lower BI. And now I'm going to split the sum into two parts, the good part and the bad part. And I'm going to deal with them separately. So in the good part, I'm going to replace capital BI minus lowercase bi with the supremum of g of y minus g of z for points y minus z that are less than delta, right? Because I know capital AI minus lower ai is less than delta. Okay. For the bad sets, I have no idea what capital BI minus lower BI is, but certainly that difference is less than 2 times the supremum of the absolute value of g. So this is a crazy bound, right? I know nothing at all about what capital AI minus lower ai are doing, but certainly I have a very silly bound on what's going on with these values of g. I just take the worst value of g for the entire interval, right? So that's certainly a bound. And just as an aside, m is less than infinity since j is compact and g is continuous. Okay, so I do need to check that m is actually a number, but indeed it is really a number. So this is sort of cool. It's something we haven't really done before. I'm bounding this thing here, and I am effectively splitting into two cases. This is a really important idea in analysis, but one that's a little bit complicated for the first course for the most part. Okay, but we'll do it here. Now I do a little bit of simplification, and I end up with this bound here. Now I'll say at this point, I haven't said what delta is, and I haven't said anything at all about p. This is a bound that's going to be true for all p and for all delta. And what did I end up with? Well, I ended up with two terms. The first term corresponding to sort of the good sets, and the second term corresponding to sort of the bad sets. And in order to get the result that I want, I need both of these things to go to zero, in some sense. Now, the first term is easy to make go to zero, right? G is continuous and therefore uniformly continuous on a compact interval. And so to make this, and this is just a number, b minus a, so to make this whole term go to zero, well, I just let delta go to zero, and then this supremum itself is going to go to zero at the same time. So that's fairly okay, right? I'm going to let delta go to zero, and everything's going to be fine. The second part is substantially harder. Here I have this sum over I of xi minus 1, and these are numbers here. There's no dependence on delta here, and there's no obvious dependence on p here, so there's no obvious way to make this whole thing go to zero. What we're going to need to do is check that actually these bad indices, even though it can be fairly large, it doesn't have a size going to zero, it can't be enormous if the partition p is pretty good. So let's do the calculation to check that that's true. I define error of p to be u of fp minus l of fp. That's the difference between the upper and lower bound function. And I'm just going to check that this is never, that this term here, that I'm sort of worried about, is never too bad when error of p is small. So I define error of p as u of fp minus l of fp, which is the sum of xi minus 1 times capital AI minus lowercase ai. So we've certainly seen this before. And now I have to do something that's clever, or at least careful, which is I want this bound here to turn into something that looks like this. So I do something that we don't do very much in this course, which is that I make a really lazy lower bound. Certainly the sum over all of these terms is bigger than the sum over just some of these terms, right? So I get this inequality, the sum from I equals 1 to n of some terms, is bigger than or equal to the sum for I in b of p delta. And then since I'm only looking at b of p delta, I can replace capital AI minus lowercase ai with just delta. It's the definition of b of p delta, right? That ai minus little ai is bigger than or equal to delta. But now I have the thing that I care about defined in terms of this function error of p that I have control over. So in particular, when I rearrange, I find this bound, the sum I in b of p delta of xi minus 1 is less than the error of p divided by delta. So I'm going to sub that bound back into my big bound star, which I calculated earlier. And I end up with the following: the upper bound g composed with fp minus the lower bound g composed with fp is less than b minus a times this supremum plus 2 times m times the error of p divided by delta. And now I'm happy because I can make this term go to 0 by letting delta goes to 0, and I can let this term go to 0 by letting the partition get good, that is by letting the error go to 0. Now, this is still a little bit funny because, of course, if I let delta go to 0 quickly, then this term is actually going to go to infinity. So I have to be careful about this, about how I'm going to relate the error of p and delta. But fortunately, that's not terribly bad to do. I just have to do things in order. So with this calculation out of the way, we're finally ready to do something that looks like sort of the usual proof. I'm going to fix epsilon greater than 0, then I'm going to plug in a bunch of values for delta. In particular, I'm going to fix epsilon greater than 0. I'm going to fix some value of delta so that this supremum here is less than epsilon over 2b minus a. I can do that because g is uniformly continuous, right? So there exists such a delta. And then I'm going to fix some partition p so that the error of p is less than delta times epsilon over 4m. And I can do that because f itself is integrable, so I can find a partition with arbitrarily small error. And the thing to point out here, which is sort of nice, is that, hey, look, error of p depended on delta, and that's totally allowed, right? I fixed epsilon first, then I chose my delta, then I chose my p. I'm allowed to do it in that order, and indeed, if you look at this error term, we better do it in that order to have any hope of getting an estimate that's going to work out. So when I do that with these choices, and I plug that into the previous bound, the proof is essentially over. So u of g composed with fp minus L of g composed with f comma p is less than, well, these two error terms. The first term here is small by this choice of delta, and the second choice here is small by this choice of p. And so I get what I wanted. All right, that's certainly enough for one video, so thanks very much.